2 covers theoretical probability. Okay, so we're just going to quickly review experimental probability. This is when you actually do the experiment. Okay, actually do the experiment. Okay, you actually do the experiment and then you take the outcomes that you get in real life. Okay, so let's recap probability. So again, probability is the measure of the likelihood that a specific event will occur. Okay, example, what's the probability that when 2 dice are rolled, both will show ones? Okay, and what is the probability that when a coin is tossed, it will show heads? Okay, we went through that. Okay, probability experiments. These can be used to estimate the probability of events such as the ones outlined above. So these ones right here. And each repetition of a round of the experience or the experiment, we should say, is called a trial. Okay, we went through trial. An event is the set of outcomes with the same result. Okay, and again, just to recap, experimental probability, this is actually the number of successful trials. So if we're looking, whatever you're looking for, okay, whatever you're looking for is a success. That's a success. Okay, over the total number of trials. Now, probability is a number between 0 and 1. And whatever the result is, if it's multiplied by 100, that would be the percentage. Okay, an example, if the probability is 0.75, well, 0.75, and then if we multiply that by 100, we get 75 as a percentage. Okay, so section 2.2, this is new stuff now. We're talking about theoretical probability, and we've already a little bit talked about it, but here is theoretical probability as a formal definition. This is another measure of the likelihood of an event, but this is calculated without performing experiments. Okay, this is very theoretical and it's based on possible outcomes. So the probability of an event, and this is for theoretical, is the number of successful outcomes, the number of successful outcomes divided by the total number of possible outcomes. Okay, so now it's possible outcomes. Total number of possible outcomes. Okay, so experimental is when you actually do it, and theoretical is when you just think about the number of possible outcomes, just in general. Okay, so to calculate theoretical probability, all outcomes must be equally likely. Equally likely. And what this means is that it means that each event has the same chance of occurring because all the conditions are fair. So for example, if we took a standard deck of cards, it consists of 52 playing cards, okay? So just a little review if you haven't looked at a deck of cards in a while, okay? The numbers go from ace to king, so ace to 10 and then jack, queen, king. So ace to 10, jack, queen, king, and that goes for four different suits. So it goes for clubs, it goes for hearts, it goes for diamonds, and it goes for spades. Okay, so let's write the theoretical probability of drawing a red king. So how many red kings are there? Well, 1, 2. Okay, so that's just simply 2 out of 52. And if we want to divide both of these numbers by 2, we get 2 out of 26, or 1 out of 26. Okay, what is the theoretical probability for drawing a heart? Well, how many hearts are there? 13, right? Ace to king, which is 10, and then jack, queen, king. So we get 13 out of 52, okay? If we want to divide both of those by the number 13, a little spoiler alert, 1 out of 4. Probability of drawing an ace. Okay, how many aces are there? Well, there's 4. 1, 2, 3, 4, 1 for each suit. Okay, so 4 out of 52 cards. I will tell you that we can divide both of these by 4, and we get 1 out of 13. Okay, not drawing a queen. So there are 4 queens, so 52 minus 4. There are 48 other cards. So the probability of not drawing a queen, and we can even write probability of not queen, equals 48 over 52. Okay, and what can we divide these by? I think we can divide these by 4. Let's try 4 at first. Yeah, so that's over 13, 12 over 13. What's the probability of drawing an ace or a face card? So we have 4 aces, and face cards are the Jack, Queen, King. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have 4 aces and then 12 face cards. So we have 16 out of 52 altogether. And let's divide those by 4. So we get 4 out of 13. That's the probability. And finally, drawing a spade, a diamond, or a heart. So how many spades do we have? 13. We have 13 diamonds, and we have 13 hearts. Okay, so 13 times 3 is 39 out of 52. Okay, and if we divide all of these by 13, we get 3 out of 4. So quite easy. The fractions might be the most difficult thing and to reduce them, but fairly an easy concept. All right, example 2. Samantha is putting posters up for a concert, and she has 12 green posters, 7 yellow posters, 21 blue posters, and 2 red posters. Okay, if Samantha randomly chooses a poster to put up first, find the theoretical probability of the first poster being green, blue, red, or yellow, not yellow. Okay, so what I usually like to do is I usually like to list exactly what I have. So we have 12 green, 7 yellow, 21 blue, and 2 red. Okay, I also like to total these up. So what does that give us all together? If we add these all up, it gives us 42 different kinds of posters, or different color posters. Okay, so green and blue are going to be very easy. Green is 12 out of the 42. Okay, which is 6 out of 21, just divided by 2, 6 out of 21. Oh, we can divide these by 3 now. 2 out of 7. Okay, the blue is 21, so simply 21 over 42, and you should be able to see that that's 1 out of 2. That's half. Okay, red or yellow. So when we see or, what we're taking a look at is the red or the yellow. We're just going to add them. So either red or yellow, we have 9 altogether, 7 plus 2. So we have 9 out of 42. And let's see if that reduces. It reduces to 3 over 14. Okay, and not yellow. So ignore the yellow. We're going to add up 12, 21, and 2. 2, 3, 4, 5, 35. 35 over 42. And what does that reduce to? 5 out of 6. Coin flipping experiment. Toss a coin 3 different times and determine all the possible outcomes using a tree diagram. Okay, so the 2 outcomes on a coin we know are heads and tails. Oops, and tails. Okay, so coin 1, you can flip either a heads or a tails. Coin 2, we're either going to flip a heads and a tails from the heads, or a heads and a tails from the tails. Okay, in coin 3, we're going to flip a head or a tails from the heads. or a heads and a tails from the heads tails, or a heads or a tails from the tails heads, or a heads or a tails from the tails tails. Okay, so these are all of the different possible outcomes that could occur. And if we count 1, 2, 3, 4, 5, 6, 7, 8, there are 8 possible outcomes. Okay, now using these possible outcomes, so I'm just going to give you a couple examples. We can roll or toss a heads, 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 tails, heads, tails, heads, heads, tails, tails, okay, and so on. So what is the outcome, or what is the probability for tossing 3 coins? Sorry, 3 tails. So tails, tails, tails. This only occurs once out of 8 possible outcomes. Okay, done. What's the probability for tossing 2 tails? So 2 tails, heads, 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 no. Heads, heads, tails, no. Heads, tails, heads, no. Heads, tails, tails. Yep, so that's 1. Okay, and you go through them. So we need 2 tails. Tails, heads, tails is another one. And then tails, tails, heads. So we get 3 out of 8 for that one. Okay, C. What's the probability of tossing 1 head? Okay, so we have heads, tails, tails, which is a possibility, and then tails, tails, heads. So that would be 2 out of 8, which is also like saying 1 out of 4. Okay, and what's the probability for tossing 0 or 1 tail? So 0 tails would be the heads, heads, heads combination, and we know that that's 1 out of 8. Or 1 tail, which is tails, heads, heads, so that occurs here. Let's do it. Tails, heads, heads. Or 1 tail, heads, heads, tail. So that would be 2 out of 8. And if we added those, it would be a total of 3 out of 8. Okay, what would be the difference between experimental probability and theoretical probability in this experiment above? Okay, if we were to actually toss heads and toss tails, in general, it's going to, like, again, we talked about this in 2.1, but the more times you flip the coin, like the 3 times, the more times you do experiments, like the greater the number of trials, so the greater number of trials, the more it's going to actually look like this. Okay, the more it will tend to theoretical probability. And let's not say it, the more the experimental probability will tend to the theoretical probability. Okay, they're going to be different numbers. It's going to definitely depend on how many times you flip it, if it's a fair experiment. Okay, but at the end of the day, the numbers will not align 100%.